Today's Matthew Morrow, and he will talk about algebraic K-theory and P-Adic Arithmetic Geometry for the general mathematical audience at the Institute.
It's not for the specialist, but it turns out to be for the non-specialist. Anyway, so the goal today is I'm going to try to present, at least in the first half of the talk, relatively elementary introduction to algebraic K-theory. And then as we get closer to the end, I hope to explain to you some of the relations to the special year, which is wrapping up now at the IAS in P-Adic Arithmetic Geometry. So algebraic K-theory is something of a reputation for being inaccessible. So let me really start at the beginning. So, very coarsely, what is this? It's what we might call a cohomology theory for rings, which more concretely means the following. It's some piece of machinery, which I'm going to define for you, which takes as input any ring R, so more precisely, that means unital and associative. So you can take, let's say, really any unital associative ring. We could take the integers. We could take the integers mod 2024. We could take the complex numbers. We could take the algebraic's circle. That is to say, take R. I join some polynomial variables x and y. And mod out by the ideal generated by the equation of the circle. I could take a compact Hausdorff group and look at integrable functions under convolution on it. I could look at bounded operators on a Hilbert space, and so on and so forth. Maybe there's an example to everyone's taste in the list. And the output of this machinery is going to be a family of abelian groups which we denote by Kn of R as n runs over the integers, and which we're going to call the K groups of the ring. And the goal of the subject is very roughly to understand these groups. Or your favorite classes of rings. Now, understand isn't very precise. Typically, these invariants, these abelian groups, which the machinery outputs, are not going to be finitely generated. So there's some enormous infinitely generated abelian groups. We don't hope to write them down explicitly in terms of generators and relations, but we hope to understand at least how they relate to other invariants that we already have at hand. We hope to cook up some elements in them and test what these elements have to do with properties of the ring, and in that way possibly say something about the ring that we were unable to say previously. And so let me try to illustrate that principle with the beginning of the story, case 0. So to define K0 for you, we start by doing some linear algebra. So my R, as I say, I take some ring R. And if you start trying to develop some linear algebra with coefficients in R, you start by looking at free R modules. You look at R direct sum R direct sum R, direct sum R, and so on. That is to say, R modules, you have a basis, and each element can be expressed uniquely as a sum with coefficients in this basis. But unlike what happens when you do linear algebra over field, then something bugs. You get projectors onto subspaces where the image of your projection might not have a basis. And you need to add these to the class of modules that you want to work with. So we say that and R module P is projective if, as I say, it occurs as the image of some projector on a module that does have a basis. So more precisely, I ask whether there exists some big enough n such that this P is sitting inside a module with a basis of length n, and there's a projector that is some n by n matrix, such that alpha squared is alpha, and so that this P is then the image of my projector inside R to the n. So as I say, one way to motivate where these come from is that you could just be naively trying to develop some linear algebra, not with coefficients in a field, but with coefficients in a general ring. And then you see this phenomenon that sometimes your module with a basis will decompose into two pieces given by this projector, the image and the kernel of the projector, and they will not have bases. So you add those to the collection of modules that you're working with. From that point of view, these are, let's say, the good modules for doing linear algebra over a general ring. And we're going to cook up from them an invariant as follows. Which was proposed by Grothendieck in the 50s. He says, let's look at all these building blocks of linear algebra over R. I can always stick two of them together under the operation of direct sum, and that equips my collection of these modules with a commutative binary operation. And I view the zero module as a zero element. So it's like a group, except I don't have inverses present. That's what we call a monoid. And now I am just going to formally add inverses. So it's Grothendieck's idea. So whenever I have a set equipped with some binary operation that looks like a group, except I don't have inverses, I can always add inverses. For each A in the set, I add an element minus A such that A plus minus B is going to equal C plus minus D, precisely when A plus C is equal to B plus D. I haven't messed up the algebra. And that produces for me a group. And that group is what Grothendieck declared to be the case zero of the ring. So some examples should clarify what's happening. Let's start with the traditional case where we do linear algebra over a field. Well, then the modules with bases really are enough. If I cut out some piece of a vector space, it's still a vector space with a basis. And it's all just classified by their dimension. So when I carry out this construction, these modules are classified by dimension, with direct summing modules be the same as just adding up dimensions. And the zero vector space is a zero dimension. So I get the non-negative integers. I carry out Grothendieck's construction of adding inverses. And I get the integers. And so the integers, we've just proved that the zeroth K group of a field is given thanks to existence of dimension by the integers. Second example. So in your first course on algebraic number theory, you study rings of integers of number fields. and you look at ideals of these rings of integers. Then some general lemma from commutative algebra, in fact, will tell you that this ideal, just viewed as a module over D, is in fact projective. And so I can associate to it some element inside the Grothendieck group of the ring. Now, what you normally do with all these non-zero ideals is you look at them under multiplication. And that's how you define the class group of the ring of integers. Or how you define the class group of the number field. And if one is more careful, what it shows is that the class group of this number field is contained inside A0 of the ring that we're looking at. And so these are supposed to be baby cases of general phenomena that we're going to see everywhere, which is why we want to understand these K groups. We stick in a field which is somehow like the most basic object of linear algebra, and the output is some basic linear algebra data. In fact, the dimension makes sense for vector spaces. We stick in some ring coming from algebraic number theory, and the 0th K group tells us about the class group of the number field. We see for free algebraic number theory information. And what's generally going to be the case is that we have this very, very generally defined machinery. You can plug in whatever ring you see on a daily basis, and the output of this machinery will be relevant information. So you stick in some ring coming from functional analysis, and the K groups will give you functional analytic information. You stick in some ring coming from topology, and the K groups will give you topological information. So in fact, let me give you a topological example. Let me take X to be a compact Hausdorff space, and my ring is going to be the ring of continuous complex valued functions on X. So I can take K0 of this ring, and what turns out to be the case is that this algebraically defined K0 of this ring agrees with the so-called topological K theory of the space X. So given a topological space, you can look at locally trivial complex vector bundles on it, purely in the world of topological spaces, and you can carry out some analog of Grothendieck's construction. And it turns out that this purely topologically defined invariant in terms of these locally trivial complex vector bundles will match the algebraically defined K0 of the ring. The key being that if you take a locally trivial complex vector bundle over the space, then the sections of it will form some module over this ring, and it will turn out to be projective. From this way, you start cooking up classes over here, and eventually it will identify the two. So in this case, we plug in something topological and we see topological information. We now leave projective modules behind. They won't appear again. And we move on to the first K group of a ring. So this is a definition that goes back to the 60s by Bass and Chanwell. We do the following construction. So we still have our general ring R, and they look at invertible matrices with coefficients in the ring, but which are arbitrarily big. Arbitrarily big, but finite. So you should imagine these are some infinite sized matrix, but where all the action is in some block in the top left corner, and then I'm just ones down the diagonal and zeros everywhere else. So I can multiply two of these. If I've got like a 5 by 5 such matrix and a 10 by 10 such matrix, I just view them both as 10 by 10 such matrices and I multiply them together. So they're arbitrarily big, but finite sized invertible matrices. So this is a horrendously big, very non-abelian group. And their idea was to make it abelian. So I mod out this group by the commutator. And that's what they define to be the first K-group of the ring.
Why did they make that definition?
Well, that's because it made sense given K0. Sometimes you want to measure the non-uniquenesses which appear in K0. But I think examples will make it clearer. No, fine. Let me first tell you. Yeah, let me first. Maybe the following lemma will make it clearer. In fact, so it's a lemma of Whitehead that tells you exactly what this quotient is. So suppose that I've got two matrices, two invertible matrices with coefficients in R. Then this lemma says that they have the same image down here. If and only if they are equivalent up to row and column operations. So a priori, this process of modding out this group by its commutator seems unwieldy, but what turns out to be the case is that you have a much more hands-on understanding of what the quotient is classifying. It's classifying normal forms of invertible matrices with coefficients in R. And that allows us to calculate it, at least in the simplest case. So let me take F to be a field again. Then we have Gaussian elimination. Gaussian elimination tells us that if you have a determinant 1 matrix with coefficients in a field, then you can perform row and column operations on it to transform it into the identity. More generally, an invertible matrix with coefficients in a field is determined by its determinant up to row and column operations. So from a K-theoretic point of view, it tells you that K1 of a field is just given by the possible determinants, that is to say, the group of non-zero elements of your field. Let's look at the second example as we did previously. I'll take D to be ring of integers of a number field. Then again, it turns out that normal forms of invertible matrices, the invertible matrices up to row and column operations, are just determined by the determinant of the matrix. Now, if D were a Euclidean domain, then you could prove this just as you did in the case of a field. The existence of a Euclidean algorithm would let you, you take one column, you see how many times it has a chance of dividing another column, you divide it in, there's some remainder, you keep going, and the Euclidean algorithm will tell you that the remainders get smaller and smaller and smaller, and the process terminates. The rings of integers of number fields are generally not Euclidean domains, not even necessarily principal ideal domains. That's what we measure using the class group of a number field. And so in this case, This is a deeper theorem of Bass, Milnor, and Serre as a consequence when they solve the so-called congruent subgroup problem. Concerning precisely structure of normal forms of invertible matrices with coefficients and rings of integer number field. So again, somehow by some miracle in the first example, we stick in a field, we see some basic linear algebra data, we see existence of Gaussian elimination. In the second example, we stick in ring of interest of algebraic number theory. We see Bass, Milnor, Serre's resolution of congruent subgroup problem. Let me now give a topological example. So I take X to be a smooth, smooth compact manifold without boundary of dimension at least 5. And the ring that we're going to be interested in this case is the following. So first, we take the fundamental group of X. And then my ring will be the group algebra of this fundamental group. Then there's a theorem proved independently by Baden, Mazur, and Starlings called the S-cobordism theorem that tells you, if I look at this purely algebraically defined K1 of this group algebra, and I want to kill the kind of the easy part. The theorem is about the hard part. And so I've already mentioned determinants. One by one matrices always give you classes here. So units of your ring, they always give you classes. So we're gonna forget about them. So I've got some plus or minus 1 coming from the units of Z. Let's forget about that. And that's also modded out by group pi itself, which is sitting in the units here. So I can kill these easily written down classes. And the theorem then states that what's left classifies H corbordisms of the manifold. So that is to say, other manifolds X prime satisfying the same hypotheses, which are linked by a cobordism with the property that the inclusions of H and H prime into this are homotopy equivalences. This geometric data is purely captured by the K1.
That's H.
Sorry?
H.
The H stands for the fact that the inclusions of X and X prime into the cobordisms have to be homotopy equivalences. So the H is for homotopy. So you can't do a sort of pair of pans construction where you have one manifold and then 2 copies of the same linked by pans, because then they won't be homotopy inclusion. Any other questions?
What is the classes?
Yeah, so I guess I mean H cobordism classes. H cobordant manifolds. Yes.
Is it more complicated for small dimension?
I have no idea what happens with small dimension. I would suspect it fails. I don't know if there's any geometers in the crowd that can answer that.
4 fails.
Dimension 4 failed. Okay.
But dimension 1, do you get something similar?
I mean, dimension 4 is the most difficult to live in, as we all know, living in a 4-dimensional space time.
What about
Dimension 1, dimension 1.
Yeah.
Surely pi 1 can't be very interesting if I'm a real manifold of dimension 1.
C'est pas les Z.
Right. Then the K1 is just plus or minus 1. I killed it. And there seem to not be any H. I guess it's true then. I guess think that it's true in dimension 1. Well, right, for sort of uninteresting reasons, because everything just vanishes. Okay, so at this point, we've defined by hand K0 over ring, K1 over ring, and I hope I've managed to convince you that if you stick in something either from linear algebra or algebraic number theory or topology, then you see relevant information in each of the three cases. But at present, the definitions are ad hoc, and what happened in the 60s was a search began for some invariants Kn of R, n bigger than or equal to, let's say 2, which we've already got, 0 and 1, which would somehow continue this chain of invariants and satisfy some similar properties. And one such property, which I think is among the most interesting, comes from a theorem of Bass, often called the fundamental theorem of K0, which states that you can recover K0 just from knowing K1, as follows. There's a K0 of a ring, which we defined using projective modules a moment ago. Identifies with a certain co-kernel. I'll spell this out in a second, because I understand that co-kernels are not everyone's daily bread. But some construction depending only on K1s. So I'm going to do the following. Let me write it down and then parse it for you. Maybe ignore the left side for a second. I do the following. I've got my ring R, and then I look at polynomials with coefficients in my ring involving both positive and negative powers of some variable. And this is the new ring that I'm going to look at. So in particular, I'm now going to look at arbitrarily big, but finite, invertible matrices whose coefficients are polynomials in both positive and negative powers of T. Horrible group. I pass the K1 by modding this group out by the commutator, but then I do some more. I also kill any matrix whose terms either only involved positive powers of T or only involve negative powers of T. The output of this construction turns out to be the same group that we defined a moment ago using projective modules. And so the punchline is that K1 is a refinement of K0, in the sense that if you know everything you want to know about K1 of every ring, then you know everything about K0 of every ring, because you have a formula to recover K0 from K1 of other rings. So let me give you a formula that you should compare this to. So if you have a topological space X, and you look at the zeroth homology of X, you can recover it from the first homology of the suspension. I think there's some extra copy of Z to stick on. So first homology of spaces is more refined invariant than zeroth homology of spaces. You could also imagine being in a situation historically in which you've managed to define the zeroth homology of space, the zeroth and the first homology of spaces. Therefore, first homology is just some abelianization of pi 1. And you were asking yourself the question, whether there existed some chain of invariants, H2, H3, H4, and so on, of topological spaces that continue to see this type of relation. And that's the situation that we were in algebra in the 60s. If we had the zeroth and the first invariant, we had a relation between them mimicking what you see in topology, and you want to continue the chain. And that's what Quillen spectacularly did. In 73, he constructed, so for any ring R, can define abelian groups Kn of R such that the same phenomenon holds, namely K, let me say this is for n bigger than or equal to 2, since we've already got the rest, such that Kn of R can be recovered, so Kn minus 1 can be recovered from a similar formula using the Kn's, to think of, as I say, as an algebraic analog of this formula here. That is to say, Kn is a refinement Kn minus 1. So we produced a family of abelian group valued invariants of rings, such that each stage we refine the one that we had previously. And I want to write down Quillen's definition of these groups for you. So we've got our ring R. Now, what we've done so far is we associated to it this big group of invertible matrices of arbitrary size. And the first step in Quillen's construction is to move us from the world of algebra to the world of topology. By taking the classifying space of this group. So that is to say, it's a connected topological space, which is essentially determined by the fact that its fundamental group recovers for me the group that we plugged in. And whose higher homotopic groups, so that is to say, instead of to define pi1, you test maps of circles into your space, and to define higher homotopic groups, you test maps of higher dimensional spheres into your space. These all vanish. So the data contained in the classifying space is no more or less data than the group itself. And now, how did we define K1? We took this group and we made it abelian. And Quillen's genius idea was that you can make sense, instead of just making the group abelian, you can make the whole space abelian in some sense. So let me say make abelian up to homotopy. This is in fact a general construction called the plus construction of the topological space that you plug in, which has the effect that on the level of the fundamental group of the space, it kills the maximal perfect subgroup. So so a group is perfect if it equals its own commutator. And general fact that any group contains a maximal perfect subgroup. There's an operation you can do to a topological space, which at the level of the fundamental group precisely mods out by this maximal perfect subgroup. Now, this lemma of Whitehead, I didn't tell you everything that Whitehead proves. Something else he proved when studying these matrices up to row and column operation was that the commutator subgroup of this massive non-abelian group is precisely its maximal perfect subgroup. So when I carry out this plus construction of killing the maximal perfect subgroup, and at the level of pi1, it precisely makes things abelian. And the punchline is that the fundamental group of the new space is precisely the K1 that by that time people had grown to love. But on higher homotopy groups, you have no control over how the plus construction behaves. So a priori, you can say very little about the higher homotopy groups of this new space that we've built. And those homotopy groups of BGL infinity R plus are what Quillen defined to be the higher K groups. And he starts his paper by writing, it is the goal of the present paper to show that this definition leads to an interesting theory, because it's not a priori at all clear from that definition.
It also sounds like the definition of BGL infinity plus could have just been take the do the things the fundamental group and then take the classifying space. It's not.
No, because then you would not pick up any higher homotopy information.
So it's something else.
But the idea is somehow you want to see some finer, higher homotopical information that was hidden when you just carried out the construction at the level of GL infinity itself. More questions?
Maybe the homology stays the same, so that's.
Did you follow?
The homology stays the same.
Yeah, the homology is true. But
So the higher homotopy groups have to change, so the fundamental group changes, so the higher homotopy groups have to change to keep the homology the same.
to define like this, I mean, these groups are supposed to be some invariants of linear algebra. I mean, we built, yeah.
Yes, I guess this theorem of Quillen maybe is probably difficult to explain, but are there at least clear maps from Kn to Kn minus 1?
No, there were not. There were not mapped. I mean, and up in this context,
Yeah, that's
fine. Here I'm asserting that there at least exists some map from there to there. That's not clear to write down.
Okay.
No, so we could go back, in fact, to the case n equaled 1. Okay, so then an object here is represented by some invertible matrix with coefficients in this polynomial algebra. And you try to express that matrix in some normal form by extracting, well, we'll try to extract some positive and some negative powers of t. You express your matrix in some normal form, and at some point what happens is a matrix with coefficients purely in R will drop out. And that matrix with coefficients in R will be a projector on some free module. And the image of that projector cuts out a projective module and defines the map. Otherwise, no, it's not clear. So let me then move on to the second theme, which is that of the special year, P-Adic Arithmetic Geometry. So from now on, we fix some prime number P. And so what is P-Adic Arithmetic Geometry? It's this mixture of number theory and algebraic geometry, where P appears really in two ways. So one is working over some ring of a P-Adic flavor. It could be FP, it could be the P-Adic integers, it could be the P-Adic rationals, it could be what is sometimes called complex P-Adic numbers. That is to say, the polynomials appearing have coefficients in these types of rings. But we also tend to only care about studying P primary invariants of these objects. When we look at invariants, like these K groups or some other cohomology groups, which are entirely of P primary flavor. So there's P appearing in two distinct ways, both appearing in the coefficients of the polynomial defining the objects that we want to study, but then we're also only going to be studying P primary invariants associated to these objects. And since they were introduced more than 10 years ago now by Schulze, the building blocks of the modern approach to P-Adic arithmetic geometry are so-called perfectoid rings. So we say that a ring R is perfectoid if it has essentially three properties. So firstly, I asked that it's p-adically complete. So that is to say, if I have some Cauchy sequence in it, where the difference between terms in the sequence becomes more and more p-divisible, then I can associate to it a unique limit in the ring. So I can perform approximation arguments by divisibility by more and more powers of p. Second condition is that it has lots of p roots. So in general, if you have an element in your ring, you can ask whether it has a p root in the ring. Does there exist a b such that b to the p is equal to a? And in the definition of a perfectoid ring, you ask that there be lots of p roots of elements. And then you ask that it doesn't have too many p roots. So it's a very subtle balance, in fact, between having enough but not having too many. You see, you've got your element, in fact, and the usual second hypothesis usually says that up to some mod p approximation, you can extract some p roots. So you pick some approximate p root, but then you can also take an approximate p root of that approximate p root by applying the condition again. And so you end up constructing in this way lots of approximate p root, p squared root, p cubed root, p to the fourth root, and so on of the elements that you started with. And then these approximate solutions can be improved using the fact that p-adic approximation arguments work in the ring. So you construct lots and lots and lots of sequences of higher and higher p power roots of your elements. And there's danger of it getting out of control. And so you impose a condition that the non-uniqueness in picking these p roots is not too non-unique. So let me give you some examples.
But this of course depends on P.
It will depend on P, because my P is fixed.
So you
Now and forever.
have a ring which is perfectoid with one respect to one P, but not perfectoid.
But as soon as it's perfectoid with respect to one P, it will never be perfectoid with respect to a different P.
I see.
Because it would fail this condition, in fact.
I see.
You can't be P-adically, you can't, yeah, these sorts of P-adic approximation arguments can't possibly work for different primes P.
Zero.
Zero. Is zero,
Zero ring.
the zero ring. Did I allow that at the beginning? No, I said all my rings are okay, it's unital and associative, so 0 is 1.
And your instruments like this.
Wait, It doesn't have lots of P fluids. Okay, but neither is this example. Okay, first example, I take finite field with P elements. Perfect. I mean, in fact, I don't mean, it is also perfect in a mathematical sense. But I also want to say it perfectly satisfies the hypothesis. P is 0, so all your P-adic approximation arguments work. And every element has exactly one P fluid. It turns out that in this particular case, every element is equal to its own P fluid, but that's somehow beside the point. Every element has exactly one P fluid. So lots of elements have P fluids, but there's definitely not too many of them. So that's perfectoid.
Why is that lots though?
Let's say every element, there's enough, because every element has a P fluid. That's pretty good. Every element has a P fluid.
Okay.
Yeah, every element. Okay, P-adic integers. P-adic integers is going to fail the second test because P doesn't have a P root inside the P-adic integers. So that's no good. But we can try to fix it by adjoining a P root of P. But that's still no good because now the P root of P doesn't have a P root. So at the very least you have to join a P squared of root, P squared root of P, and so on and so forth. So you end up adjoining all P power roots of P, the ZP. Now you stand a chance of being perfectoid, but it turns out that you've failed the first hypothesis. In fact, you've added so many elements that you're so far away now from the P-adics that you're no longer complete. But that's just a minor blip, and so you complete your ring with respect to some P-adic topology, and the day is saved. Now, if we had some perfectoid ring, okay, we could take it to be this one. We could try to add a polynomial variable. But then again, it's not going to work because the polynomial variable x is not going to have a P root. So we better at least try to save the day by adding a P root. But then again, now the P root doesn't have a P root. So we add a P root of the P root and so on and so forth. We add all P power roots of my variable. The coefficients, there's lots of P roots there. In the variable, there's now also lots of P roots. There's the same minor blip as in the previous example that I'll need to fix some topological completeness issue, but it's not too important. That will then be perfectoid. And so in general, the recipe goes as follows. I mean, what do we want to study in P-Adic arithmetic geometry? We want to study some object defined by some equations. And the coefficients of these equations are going to live, let's say, in the P-Adic integers. So geometrically, we're in the following type of context. You have some polynomials f1 through fb, the coefficients in the P-adics, and some number of variables x1 through xa. And you now try to cook up some perfectoid rings. You add P power roots to all your coefficients. Maybe you extract P power roots of all the polynomials which are appearing. you have the variables which you're pairing. You have to worry about what you do with the polynomials. Let me forget about that. By some recipe, you end up cooking up a bunch of perfectoids. And in fact, you end up cooking up, in some precise sense, enough perfectoid rings. And this is the sense in which I wanted to say that they can serve as building blocks. That if you want to study some question in P-Adic arithmetic geometry, typically you have enough perfectoid rings to govern the situation. And so if you can, it's not quite true, I'm exaggerating a little bit, but if you can completely understand what's going on with the algebra of perfectoid rings, you can begin solving problems in P-Adic arithmetic geometry. And so I want to finish by telling you that even though a priori, I mean, they have nothing to do with one another, there's some very nice interaction between algebraic K theory and P-Adic arithmetic geometry through perfectoid. And I've chosen two results to do that. So the first, here's a question you can ask purely on the algebraic K theory side. So we've got some ring. Is it true that the K groups of the ring are unchanged when we start adding polynomial variables? So it's some precise way of asking whether linear algebra with coefficients in a polynomial algebra just collapse to linear algebra over the coefficient ring. And a large part of the interest in this sort of question stems from the result that Quillen proved when he defined these K groups, which is that it's true if R is Noetherian, so it satisfies some standard finiteness hypothesis, and non-singular in a suitable algebraic sense. So you look at the dimensions of some algebraic cotangent spaces associated to your ring, you ask that these have the correct dimension, and then you declare your ring being regular, chosen to write non-singular instead. And under this non-singularity condition, then linear algebra somehow indeed simplifies, even if you start adding polynomial variables. And there's a conjecture of Wurst from the late 70s, which is proved in many, many cases, which says, which establishes the converse, again, under this finiteness condition. So if I'm Noetherian and singular, then this should fail. So you can detect singularity or not of your ring purely by looking at K-theoretic information. Now, perfectoid rings, since we've got these massive numbers of p-power roots of elements, typically fail terribly to be Noetherian. Nevertheless, one can prove that perfectoid rings, there's a slight caveat, but let me forget about the caveat. One can check that from the point of view of K-theory, perfectoid rings behave as though they're non-singular, is the punchline. They behave as nicely as non-singular rings from this point of view in algebraic K-theory. So many of the pathologies that one might see in algebraic K-theory of arbitrary ring does not occur within these building blocks of P-Adic arithmetic geometry. The second statement I wanted to give which is really a combination of two theorems. First, joined with Bagger and Peter Schultz, so the second joined with Dustin Clausen and Akil Matthew. So again, we're going to take some perfectoid ring, or in fact, some nice, here in this case, it's particularly important that it could also be a suitably nice quotient thereof. Then these algebraic K groups, a priori defined in a very linear algebraic manner, can be expressed in terms of so-called prismatic cohomology. So prismatic cohomology is a sort of ultimate cohomology theory in P-Adic arithmetic geometry at the moment. Introduced by Black and Schultz. So I said at the beginning that in P-Adic arithmetic geometry, we're going to be interested in some P primary invariants, some P primary cohomological invariants. And these are typically things like Ital cohomology, Duran cohomology, and crystalline cohomology. But you have this prismatic cohomology that is wrapping them all together at once, and which allows you to detect even the algebraic K theory of the ring. So in this way, you get some information flow in both directions. You can study this cohomology theory using K-theoretic methods, but you also got feedback, because this is typically more calculable, into the K-theory direction. And because of these types of results, there's some simultaneous interest in K-theory especially. I'll finish there. Thank you.
There's very nice lecture. So the questions.
So at the beginning, you told us that we can put our arbitrary ring in Kn. If I remember correctly, if we put a C-star algebra, we know that K2 is K0. Is it clear in this?
No. In fact, I'm not even sure that's true for the completely algebraically defined. And with finite coefficients, it should be true. There's also a topological variant of K theory for C-star algebras.
Okay, maybe so.
And now it's certainly true. Certainly true.
When the ring has a topology, there are other variants. Let us use it for the.
There are variants which stand some chance of seeing the topological data. Yeah. Which there was some ongoing efforts to uniform these variants using condensed mathematics.
Any other question?
Bit of a small one. This result that says that when you join like a polymer ring to a perfectoid ring, and that the K3 is just the same. Is that also true if instead of joining a polymer ring, I did some more complicated construction that stays in the perfectoid land?
To do some complicated.
Like example 3 that you have over there, like where you like join all the P roots of X and then completed. Is it also true that the K3 of that is the K3 of R?
That doesn't sound like it should be true. In fact, the P completion at the end looks like it should mess things up. But if you've gone, right, no, it sounds like the P completion at the end would mess things up. I'm not sure that's something you would want to be true anyway. No.
How does the K theory of a perfectoid ring compare with the projective limit of its quotients mod P to the n?
Okay, it's so the little lie that I allowed myself here is that one is not going to see all of the K groups of the perfectoid ring. You're only going to see the P primary information inside it. The K groups with mod P power coefficients. And if you restrict attention to that, then it turns out to be isomorphic. At least for the positive K groups. Again, existence of negative K groups, I swept under the rug. But for the positive K groups, that will be true. And that will be another consequence of this work. Thank you.
Okay, so let's thank our speakers.